This lesson is a continuation of calculating equilibrium concentration. We did this example in the previous video. We're now going to do the last example in your note. Let's finish off our examples of calculating equilibrium concentrations. And let's look at a similar reaction, but with some different data given to us. So we have a reaction of hydrogen and fluorine in equilibrium with 2 moles of HF. We know the K value. This now is using the symbol Kc, which is just another way of symbolizing the KEQ value. So sometimes the C stands for constant, so equilibrium constant. Typically, though, we use KEQ, you're going to see both. So we notice it's a little bit of a bigger number, right? It's 115, which tells us that we're favoring products. And then they tell us that we're putting in 3 moles of hydrogen, 6 moles of fluorine into a 3-liter container. What are the equilibrium concentrations of everybody? So this is similar to the previous question, but a little bit different in terms of the data that is given. So as usual, we want to calculate the concentration of our reactants. And again, as we read this, they're taking this hydrogen and this fluorine gas and they're placing it in a 3-liter container. These are initial concentrations. They do not state that they're at equilibrium. So we're taking moles over our volume, and we have 3 moles divided by 3 liters. So we're just going to sub that in, and we're going to get 1 mole per liter with a lot of precision. And then we're going to do the same thing for fluorine. So again, initially we have moles divided by my volume in liters. We now have 6 moles divided by the same volume of container. And now I get 2 molar or 2 moles per liter. You can use either unit, doesn't matter. So now let's set up our ice chart because we need to know equilibrium concentrations and we don't have any of those. So we always rewrite our reaction out. Again, you can leave states out because we know that they're gases. Okay, this is what we're studying at the moment is gas equilibrium. So you don't need to put the states in. We have our initial amount, our change, and then whatever we get at EQ or equilibrium. So for hydrogen, we have 1 molar. For fluorine, we have 2 molar. And then initially for those products, we don't have any of them. They don't say that there's any in that flask, so we assume that there's nothing. Over time, those reactants are going to decrease by the same amount simply because their molar coefficients are 1 to 1, but the HF will increase by 2x. So at equilibrium, we have the initial minus the change, and same thing for fluorine. So 2.000 minus x. And then for my product, the initial is 0. And then we apply the change, which now is a plus 2x. So at equilibrium, I just have 2x. So let's set up the KQ expression. And we know that this is equal to products, so HF squared, divided by the concentration of my reactants, both to the power of 1. And then we will set this up. So KQ, I'm going to get it out of scientific because I don't like it. And then I'm going to have 2x squared in the numerator divided by 1. I'm just going to leave it as 1 right now. I'm going to worry about all those significant figures a little bit later. Okay, so 1 minus x times 2 minus x. And similar to the last equation that we did, or the last example that we did, it's a similar reaction, okay? But what's different is that down here in the denominator now, I don't have the exact same terms. So I'm going to have to multiply those through, and we can start that over here on the other side. So just follow along. We've got 115. We're going to expand the top. So 2x squared is equal to 4x squared. And then we have to use, expand all of these. So we're going to take 1 times 2, which is 2. 1 times negative x, which is negative x. And then we're going to take negative x times 2, which is negative 2x. And then we're going to take negative x times negative x, which is equal to x squared. We're going to group all of these around. So we're going to take everything in the denominator and we're going to cross multiply by 115. So the first thing that we'll do is we'll just clean this up. So we'll do 4x squared, and then we're going to divide by 2 minus 3x, because we're going to group these terms right here. And then we're going to have plus x squared. So 115 times 2 is 230. 115 times negative 3x, oops, 115 times is negative 345x plus 115x squared. And then I'm just going to bring, or actually I'll leave it here, is equal to 4x squared. And then now let's bring our x squared term over so that we can group everything. So I'm just going to rewrite this, 345x. And then when we bring our 4x squared over, we'll be subtracting it off. So we're going to end up with 111x squared equaling 0. So you can see that we have set up a quadratic equation right here. And we have to solve for x because we need to know our equilibrium concentrations. And once we know x, we can apply that into our equilibrium line of the ice chart. So we're going to first start by setting up that quadratic. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And you guys should know that the a term is your x squared term, b term is the x term, and then the c term is the non-x term. So go ahead and sub that in, and then take a second and solve for x. Make sure you do this in baby steps because it is easy to make an error when you do the quadratic equation. And also be aware that there is this plus or minus term in the middle. You need to come up with 2 x values as a result. So once you solve for both of your x terms, again, keeping in mind that there's a plus or minus in the middle of that quadratic formula, you're going to have 2 values here and you're going to say to yourself, which one do I need to use? Well, you have to go back to the ice chart and you have to take a look at the equilibrium line in your ice chart. And remember that this x term is the change in concentration over time. Well, you cannot have a change in x that is larger than your initial concentrations. So when you look at your initial concentrations of 1 molar and 2 molar, you realize right away you cannot use this x term because it is larger than your initial concentration. So we discount that one, and this is the x term that we need to use. And then we keep on going for step 4, and we calculate our concentrations of our substances at equilibrium. So once you sub in all of your values for your reactants and your products at equilibrium, there are the concentrations that you get at equilibrium.